So we want to look at the concept of complex numbers. Now, complex numbers is not really a complex topic. Let me put it that way. So, because when you look at the topic complex, now the word complex in itself have two different meaning. But since it's a mathematics topic, one thought or one conclusion, the first impression of this word is that it's something complicated, though. But complex can also mean the combination of two parts. So when we say a complex, we're talking of kind of compound, a compound. So a complex is kind of like a building. We can have a building where they sell a lot of things. It's a complex. So why we call such a building a complex is because you have different shops in that building, and those different shop they render different services or they sell different services. So it's a combination of two or more parts. That's when we say something is complex. So the opposite of that is simple, as we know. So when we say something is simple, we mean it's just individual, it's just one particular thing. But when we say something is complex, in this case, we're not talking about something that is complicated. So it can also mean complicated in an English sense. Say it's such a complex question, complicated. But in this case, it's not. That's not what it means. So it just means a compound, the combination of two or more parts. So and when you look at the way a complex number is usually denoted with the letter Z. We can and write Z is equal to A plus BI, something like this, A plus BI. So this I sometimes, let me say, or we can say Z is equal to A plus BJ. It depends. So some people use I, some people use J, but I would like to stick with I because the I actually stands for imaginary. So the Z is just a letter. You can use any letter, but Z is actually the convention. Our A here is representing the real part. The real part. Remember, I said from the start that a complex is a combination of two parts. That's why it's not simple. It's not a simple number. It's a complex number. The BI here, let me say the BI here is the imaginary part. Imaginary part is the imaginary part. So now, when we say real, we're talking about that the number belongs to the set of real numbers. So when we talk about real numbers, we're looking at our fractions, our decimals, our rational numbers, even our irrational numbers. So all numbers we've been used to, our natural numbers, they are all part of the set of real numbers. Like for example, let me just say, for example, 3 is a real number, 1 over 4 is a real number, pi is a real number, and you know pi means 3.14. E is a real number, which is an exponential function. The same way we have pi as a special number, we have E as 2.17, also a special number. So these are examples of even root 2. These are examples of real numbers. But when we look at the imaginary part, I will explain it later. But now we can if we say I is an imaginary number. So, but in this case, we can use I or J. In this case, let me pick an example of a number. For example, I want to just explain something that is a bit, I would say, a misunderstanding in a sense. Let's say we have Z is equal to 3 plus 7I. Good. And somebody asks you, say, what is the real part of this number and what is the imaginary part of this number? Now, the real part, which is usually written as uh, R of Z, RE of Z, the real part is 3, like we said. You can see there's no I attached to it. But the imaginary part, which is Im, this is the way we write it. The imaginary part, Im of Z. The imaginary part is written as 7. That is the correct answer. So why I'm saying it's a misunderstanding is because 7 in itself is a real number. So it's like a confusion, but it's the convention that we should just take it like that. So If I were to say what is the imaginary part, I would prefer to say it is 7i. That's if I'm to speak for myself, or I'm to speak my mind, I would prefer to say it is 7i. Or in fact, it's I. That was why I wrote I here. I prefer to say it is I. I is the imaginary part. But the convention is that you write the number behind the I, 7. So some another convention that you will see is that this type of number now, some people usually write it as 3 plus the 7i, they will write the I coming before the 7, or 3 plus if it's J, you write the J coming before the 7. So you have several conventions like this. So complex numbers, just like any other real numbers, can be added, can be subtracted, can be uh, can be multiplied. They can even be divided by one another. So let us say the addition is the simplest part. If we are to add 3 3 plus 7i to we are to add it to minus 5 minus 9i, something like this. So the addition is just you add the real to the real and you add the complex to the complex. So sorry, you add the real part to the real part and you add the imaginary part to the imaginary part. I won't call this the complex part, I'll call it the imaginary part. So together they make a complex whole. That's what it should be. So I'm going to say 3 plus 5, which gives me 8, and I'm going to say 7 plus 9, which gives me a 7 plus minus 9, because this is having a negative, the 9 is having a negative side, so it's more like 7 plus minus 9, or minus 9 plus 7, which will give me minus 2. So I'm having minus 2i. So very simple, real plus real, imaginary plus imaginary. If we are to subtract, of course, it's just the same, but in fact we did a kind of subtraction here. Only that the first one was smaller. So if we are to multiply 3 plus 7i, let's just say the same number, by multiply by add to by 9 plus 9i. If we are to multiply these two numbers now, the method is multiplying is just our normal expansion method. We multiply as though we were expanding algebra, algebraic expressions. So this is not algebraic expression, but if you see it for the first time, you would think it's an algebraic expression actually, if you are not familiar with with a topic called complex numbers. So, but you just take it as if you are dealing with algebra and you multiply. You use your FOIL method. 5 times 3 or 3 times 5 is 15. Then we go again, we say 3 times minus 9 is minus 27i. Okay, and we use the second number, 7i times 5 will give me plus 35i. So you have to be very careful so that you won't make any mistake. Okay, I think we are right so far. Then you go again, 7i times minus 9. I know I'm going to be having a negative value. 7 times 9 gives me 63. Okay, and I times I in two places gives me I squared. Now this I squared on its own it has a value of minus 1. Now we'll explain what this means. Maybe that's where I'll end the class for today, or I might go further depending on how much time we have. So of course we're going to simplify this. We have 15 minus 27 plus 35. I think we'll be owing 8, so that'll be plus 8i. All right, minus 63. Remember we said I square is giving us minus 1. So if we simplify this, our final answer is 15 plus 8i plus 63, because minus times minus is plus. And when we add this, since they are both real parts, we get 63 plus 15, which gives us 78. So this is 78 plus 8i. So this is our final answer in this case. Okay, I will come back to division later, but let me just digress a bit, divert my teaching a bit to explain this interesting thing that I put here. So how is I squared equal to minus 1? And that is what I want to quickly explain. Good. All right. Um. All right. So now the idea of imaginary number I believe the best way I can use to introduce the concept of imaginary number is to take us back to our to when we are factorizing quadratic equation. Now, there's a part that is usually, remember, if we use a quadratic formula, our quadratic formula, I hope we remember our quadratic formula. What does our quadratic formula say? Quadratic formula is minus b plus or minus x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. I'm not going to pick out any particular equation to factorize now using this because of time, but I'm going to take this discriminant. Remember, this value inside the root form, we call it the discriminant. Okay, discriminant, and we said this value is very, very important, but I don't want to go into that. So, but if we pick it out, b squared minus 4ac, let us say we have b squared minus 4ac to be negative. So when I say negative, I'm talking about examples like e.g. the square root of minus 17. This is what I said is negative. The discriminant itself, square root of minus 17, square root of minus 20, square root of square root of minus 25, something like this. So we usually say the number does not have real roots when we are factorizing and we get to this stage and the discriminant is negative. In fact, most of us stop there. We just write no real roots, no real roots. So, but there are no real roots, but it can be further simplified. If we pick out this third one, for example, and say the square root of minus 25, remember from sorts, this square root of minus 25 can still be written as 25 times minus 1. I want to break down this surd because this is a surd only that it's negative. So it's actually rational because 25 can be, of course, we can take the square root of 25. So this is more like a legit surd. This one is also like a legit surd. So, but if you call this a surd, this third one, you're half right. So, but let's keep those argument for another day. Let's focus on this one. Surd rule, when we're simplifying surd, says that we can break this into root of 25 times root of minus 1. You see how we are simplifying this guy into this? Good. Now, this root of 25 is going to be 5 times the root of minus 1. The root of minus 1 cannot be solved. It cannot be found. You cannot get the square root of minus 1 because the square of any number will give us a positive number and we're having a negative number. In short, nothing will multiply itself to give you negative 1. Let's put it that way. So it is this number here that cannot be further simplified that we call an imaginary number. Mathematics is quite interesting. Believe it or not, there are important topics in engineering and maths where these imaginary numbers are useful and are needed. So it's called imaginary number and we denote it with that I or J. So hence we'll now say this is what? This is given as 5i. So this is what I is representing. So therefore, I, anywhere you see I, you know that I is equal to minus 1. I is equal to minus 1, and you can see that the square of I, so this is what we call powers of I. If you're studying complex numbers for the first time, you are going to have to know your powers of I. The square of I is going to be equal to minus 1 squared, and your square will cancel your square root and you have minus 1. And if we keep going, we can take our power even further. Say the cube of I. The cube of I is going to be what? It's going to be, we can say the square of I times another I, because based on indices, this is having a power of 1 and multiplication in indices is addition of the powers. So 1 plus 2 is 3. So this makes sense. So since we know this, we say I squared already is minus 1. So that's minus 1 times I. Minus 1 times I. And minus 1 times I is minus I. So how about I to the power of 4? I to the power of 4 is going to be what? It's going to be I squared times I squared. And what is I squared? I squared is already minus 1. And when you multiply it by another minus 1, you get 1. So these are the basics. Even if you just go one further, I to the 5, I to the 5th power will be I to the 4th power times another I, and I to the 4th power is a positive number 1, and when we multiply by I, we just get I. So now you see that even though in itself we started by saying that the imaginary number I is it looks very difficult to be simplified, which is in fact impossible to be simplified. The powers of that imaginary number start giving us interesting values. For instance, the square of that imaginary number is giving us a real number. It's purely real. When we take that imaginary number to the 4th power, we also have a real number, which is 1. So that is where these topics get interesting. I'm going to stop this one for now, and we are going to create another video where we'll look at expressing complex numbers on a graph, on a graphical, using graphical representation, and expressing complex numbers in polar form.